Do you feel like a coffee break? So do I. What about we talk about a game you may have heard before, the countdown game. Talking about a game during coffee break, that could definitely work. Especially when solving it will take you through many features recently added to the JDK that you may find interesting. So you will hear about records, cell types, pattern matching, unnamed pattern, that's a new feature from the JDK 22, exhaustive switches, mapMulti, that's a method added to the Stream API in the JDK 16, and gatherers, and that's also a new addition to the Stream API, still in preview as of now. And as a bonus, we will solve this game in a very elegant and efficient way. This countdown game is quite an old game, as it was created on French television in 1965, and by the way, is still active as of today. That was almost 60 years ago, and adapted to the British television, where it's still active also, in 1982. The principle of the game is very simple. You draw some numbers, 6 of them, and there are 2 sets of numbers you can draw them from. The first one is called the set of large numbers. It is made of a 25, a 50, a 75 and a 100. And then there is the set of small numbers, and there are 20 of them, with 2 of each, 1, 2, all the way to 10. And when you draw a number, you can choose to draw it from the set of large numbers or from the set of small numbers. So if you choose to draw 4 numbers from the large numbers, then you know in advance that you will get 25, 50, 75 and 100. When you have drawn all your 6 numbers, another number is randomly chosen between 100 and 999. And the challenge is now to find how you can reach this last number by combining the ones you have with the 4 operations. And there are a number of rules you need to follow. First, you cannot use your numbers more than once, which seems reasonable. You cannot use negative numbers, and you cannot use decimal numbers. And then you have 30 seconds, which is really short. And it's really amazing to see how people can solve that. This problem can sometimes be really tough. The question I would like to solve is the following. How can you write an algorithm to find all the solutions for a given problem? And could it be possible to make it efficient? And we will talk more about what efficient means. It turns out that there are many resources on the web, including on YouTube, that are solving this problem. And that a very interesting post has been made on inside.java. The link to this article is in the description. And by the way, if you don't know this website, I really encourage you to visit it, because there is a lot of very interesting technical articles posted on it. What the author is doing in his article is translating a piece of code written in Haskell that is solving the problem directly to Java. Why is Sundar doing that? Well, Haskell is a language designed from the ground up as a functional language, with a very elegant syntax to describe sets and operations on them, as well as functions. Sundar chose a video published by Professor Graham Hutton, in which he writes a piece of Haskell code to solve the countdown problem. The result looks really nice in Haskell, with a very compact and clean syntax to describe the solution of the problem. And with the features recently added by the project Amber to the Java platform, like records, cell types, and pattern matching, one could wonder what it would look like to write the same code in Java. So this is exactly what Sundar is doing, and the result is actually pretty amazing. You should definitely check it out. All the links are in the description. So what can we do from here? Well, first we can analyze the algorithm and see if we can do better. That is, answering the question, is it efficient? And if not, how can we improve it? The fact is, there is no smart algorithm, no fast algorithm to solve the countdown problem. Whatever approach you choose, you need to brute force all the possibilities to find all the solutions. So let us first analyze how the Haskell code is solving the problem. In a nutshell, what it is doing is create the set of all the possible ways you can combine the numbers you have with the 4 arithmetic operations, under the constraint that all the operations should be valid, and then keep only the ones that give you the right result. Seems like a good pattern for the Stream API, but it may also sound daunting because you have many combinations. But in fact, it's not too bad because there are only 6 numbers and 4 operations, so any modern computer can handle that in a matter of milliseconds. First, you compute all the possible subsets of the numbers you have. This method is called subs in Sundar's code, and for 3 numbers, it would give you the following. Second, you compute all the possible permutations of the numbers in each set. And you do that for all the subsets you have. The method which is doing that is called choices. It calls internally the perms method. Calling the perms method on the following set will give you the following result. Basically, you have all the permutations of the set. Calling choices actually calls perms internally on all the previous sets. So calling choices on the set 1, 2 gives you the following results, and calling it on the set 1, 2, 3 gives you more results. And it may seem dangerous to conduct this extensive search because there are factorial n permutations in a set of n elements, and the factorial grows pretty quickly. But we have only 6 numbers, so that's actually 720 permutations, which is really okay to handle. And if you compute all the choices with 6 numbers, you will get a little less than 100,000 different choices, which is also okay. At this point, you have a set of ordered sets with all the possible permutations of all the possible subsets in your original set. So the next step consists in applying your 4 operations on them. And for that, each ordered set is split in 2 groups. All the different ways of splitting your set are taken into account, something like this. Here I'm showing you an example with 6 numbers. You can see that you have 5 ways of splitting your ordered set. So in the end, that's again a lot of sets. And then the third step, which is actually computed along with the previous one, consists in applying an operation between the 2 groups you have. So for each group, you generate 4 candidates. Of course, there are cases where you cannot compute the result yet. If the group is just a number, then you can, but if it is composed of several numbers, then you need to go one level deeper and apply this algorithm again on this group recursively. And indeed, this is done recursively, both in Haskell and in the Java code that Sundar wrote. This is the results method, and this is the result for 2 elements in your set. As you can guess, there are much more results with 3 elements, 96 to be precise, and much more for 6 in the order of 300,000. Once you can resolve all the groups you have, all you need to do is filter the results. And filtering is done in 2 steps. First, you remove all the operations that are not valid, subtractions that would give you negative numbers, division with a non-zero remainder, or divisions by 0. That's for the first set of rules, the ones you need to apply following the rules of the game. But you can actually consider more rules. For instance, it does not make sense to multiply or divide by 1, so you can discard these. And then it does not make sense neither to subtract equal numbers. That would give you 0, and there is nothing you can do with a 0 in this game. So that's another one you can discard. And because the addition or the multiplication are commutative, you can also decide to keep only these operations if the left operand is lesser or equal than the right operand. And that's it for the second set of rules you can apply to discard some of the operations. So in the end, the code is actually super simple. First, you compute all the choices. Then for each choice, you compute all the results. And all you have to do now is to compute the value of this result and select the corresponding result if the value matches the target. And the last step just consists in building the string of characters so that the result can be displayed properly. The subs, perms, choices, and results methods are interesting to analyze, but they are manipulated streams of data, so nothing really typical of data-oriented programming in them. There are two elements in this code that really leverage the data-oriented programming features, which are the handling of the results and the one that generates the string of characters. First, the result object itself is a record. It is built on an expression object and a value, the value being the evaluation of the expression. Because the result can be built on values or operations, this expression type is actually a sealed interface with two implementations, the first one being a record value and the second one a record operation. This value record actually wraps an integer, and the operation, which is called app, is built on an operator, which is an enumerated value, and two other expressions. One method fully leverages this data-oriented approach, the method that is composing the expression into a string of characters. This method is called brac, and it is built on the following switch, and by the way you can also write it in that way, leveraging the fact that now the compiler can tell you if your switch is exhaustive or not, and if it does need a default branch or not. And as a rule of thumb, try to avoid writing default case in your switches. Remember that this code is a translation of a piece of Haskell code, and there are several things that could have been written in a more Java-ish way. So that's almost it for this part. One question you could ask yourself is the following: is this algorithm efficient or not? And by that, I don't mean the implementation. If you use parallel streams, it will make your code faster, probably. If you use arrays instead of stream, it will make your code horrible to read, but also probably faster. And this is not what I have in mind. By efficient, I mean, is this algorithm exploring this set of all the possible ways of combining your original set of numbers in an efficient manner or not? The set of all the combinations is explored using a top-down approach, so you are exploring operations that will prove not valid, but you know that only when you have reached the bottom of the tree you are building. So you will be exploring invalid operations again and again, which is inefficient. How can you see that? Well, suppose that you have only three numbers, a, b, and c, and that you cannot divide b by c. For instance, b is 1 and c is 3. Well, you will still examine the four possibilities: a plus b divided by c, a minus b divided by c, a multiplied by b divided by c, and a divided by b divided by c. There are cases where you will not, because another invalid operations will be detected before, but in the worst case scenario, this will happen. Actually, you can count the number of invalid operations this algorithm computes. And this number does not depend on your target number, it only depends on the numbers you have to reach it. So for the set 25, 50, 75, 100, 1 and 10, which is a realistic set, this number is a little more than 1,100,000. And if you check the number of different operations, it's only roughly 85,000. So yes, maybe you can do better than that. This top-down approach, where you compute all the possible combinations and permutations and invalidate them at the end, doesn't really give you any wiggle room to check if a branch of this tree can or cannot give you a solution. You can only know that when you see all the branches, and at that time it's too late to avoid all these useless computations. So let us take it in the other way and see if we can do better. And let us see if we can use more elements of data-oriented programming. First, let us make this program simpler. Suppose that instead of having 6 numbers, you only have 1. Checking if this number matches the target is pretty straightforward. You just need to check if it matches the target, that's it. It's not really a problem. So suppose now that you have two numbers. Well, you need to check the four operations that give you four numbers, maybe less actually, because the division may be invalid. And now you have four problems with one number that you solve in the previous step. Great. Suppose now that you have three numbers. You are able to solve the problem if you have only two numbers. So how can you make it a two numbers problem? Well, you need to take two numbers from the three, apply each operation, and then you have a problem with two numbers that you solved in the previous step. You can even make your problem a little simpler by adding a constraint, which is that your numbers should always be ordered in the decreasing order. That will make most of your subtractions valid and eliminate many invalid divisions by design. In a case of three numbers, you have 12 problems with two numbers, as you can apply four operations on each of these three sets, and you may even be able to discard some of them if they are invalid. In this last example, you can see that an operation can be applied on two kinds of elements, a number and another operation, just as in the Haskell solution. You need to keep track of the operations you're doing, because at the end, you will need to create this string of characters, and you will need this information for that. So you can use the same approach as the previous solution, create a sealed interface with two implementations, number that wraps an integer value, and operation. And you have four possible operations, because we are using four arithmetic operators. So you can create another sealed interface to model that, with four implementations corresponding to the four arithmetic operations. This design will certainly work, but we want to avoid repeating the same computations again and again. And for that, we need to store the result of a computation along with this computation. So let us modify our record to add this component. I know it's not very nice, but let's do it anyway. Now, suppose that you have a list of elements and that you need to merge two of these elements together. How is this algorithm going to work? First, you need to remove the two elements from the list and generate the four operations, discard the ones that are not valid, and suppose that the division is not valid, and then insert the result at the right place to keep the list sorted in the descending order. So that's several precise features that you can implement using some of the last methods added to the Stream API. Let us write the first step. So suppose that you have the elements you are working on in an elements object, and you have an enumeration called operators, and you have the two indexes, left index and right index. You can first stream the operators and apply each operation on the two elements left and right. But as you saw, this operation can be invalid. So it's not really a mapping, it's a mapping that can return something or can return nothing. How can you implement that? The first solution that may come to your mind is to use optionals, and it works nicely. You can open your optional with its stream method in a flat map call, and all your empty optionals will magically vanish from your stream. And you can also do it with a plain stream in the exact same way. These are the classical way of mapping with a validation. But the JDK 16 brought a new solution, better than these two, where you do not need to create this optional or stream object, which is an overhead. This method is called mapMulti. Let me show you how it is working. This mapMulti method takes a bConsumer. The first element of this bConsumer is the element of the stream that you may decide to process or not, and the second element is just the downstream as a consumer. You can decide to call downstream accept with your mapping or not if you don't want to. Let us write this method call. First, you need to build the operation from the operator. And this is a switch statement, and because you switch on an enumerated value, the compiler can see that this is exhaustive, so you don't need any default case. The first case is the addition, and there is no addition that is not valid, so in this case, you always pass the result to the downstream by passing it to its accept method. The second case is the subtraction. Your stream is sorted in a decreasing order, so left cannot be lesser than right, but they can be equal, and you don't want to generate any zero in your stream, so you need to discard this case. Note that you are using a resolve method there, because left and right are elements. They can be just a number, but they also can be an operation. So at some point, you will need to write this method. Then you need to handle the multiplication, which is interesting only if you don't have 1, because multiplying by 1 is not interesting in this game. And then there is the division. First, the division is valid only if the remainder is 0, and you also don't want to divide by 1. So here is the final version of this mapMulti method call. You can make it even more efficient by inlining the computation of operation, since it's not used in all the branches. This mapMulti method was added in the JDK 16, so quite recently. And it's really a great addition when you need to do exactly that. I love it. We left aside the implementation of this resolve method, and we need to write it at some point. And because element is a CIL type extended by another CIL type, namely operation, you can now use a switch expression without a default branch and deconstruct each record. Note that you can use the unnamed pattern, a final feature of the JDK 22, to tell the compiler that you are not going to use a specific pattern variable. And this is a great addition, because initializing the value of your patterns variable actually calls the accessor of your record, which may be costly if you're doing some defensive copy, for instance. We chose to add the result of a computation in the operation records. If you don't want to do that, then you can write a recursive solve method in that way. But you will be computing these results again and again each time you traverse your trees of operation, so it will not be very efficient. At this point, you know how to merge two specific elements of a list of elements. Now you need to add the result of this merging as an element to a sorted list. So let us do that. Let us insert an element in a sorted stream. A naive way to do it would be to add this element at the end and to sort this stream again with the following pattern, for instance. This is the classical way of doing it, and it's probably better than using string concat, which can fail if you have too many nested streams, which is not the case in this example. But it's also pretty inefficient since the existing stream is already sorted. What you really need is inserting this element at the right place. And there is no way you can do that directly with the Stream API. Well, until now. Because in the JDK 22, you have a new API called the Gatherer API that you can use to solve this problem. I'm not going to deep dive into this gather method and explain you all the details of the Gatherer API, at least not now. First, it is still a preview feature, so it may change before making it as a final feature. And more importantly, my friend Nikolai already did the job. He did 2 videos on the subject, so please check them out, the links are in the description. We are going to use the gather method of the stream interface that takes a gatherer as a parameter. And we're going to build a gatherer object that can do exactly what we need: insert an element at a specific place in a sorted stream. There are several ways to build a gatherer, depending on what you want to do with it and how it behaves. Here we are building a sequential gatherer, and there is a factory method to do that. How is your gatherer working? Well, first, it needs to know the elements you want to add to the stream. Then it will receive the elements of the stream, one by one, and check if it is the right time to insert this element. If this is the case, then it does, and continues to pass the elements until the stream is done producing elements. To implement that, a gatherer is built on 3 elements. The first one is an initializer, because a gatherer can be built on a state and even on a mutable state. The state you need in this case is the element you want to insert. The second element is an integrator. It is used by the API to give you the current element of the stream and the downstream. You need to call downstream.push and pass the element you want to pass as an argument. This push method may return false, and in that case, you know that no more element is accepted by the downstream. This is useful if you have an intermediate method like limit, for instance, after your gather method. It is also important to propagate this value to the upstream, reason why you need to return this value. And this integrator also takes your state object as a first argument, meaning that you can check this state and mutate it if you need it. And by the way, this is what we are going to do here. First, you check if the current element is lesser than the element you want to insert, and if this is the case, well, you pass this current element. But if it's not the case, then you need to insert your element and keep the current one for the next call, and you can use the mutable state of your state object. And then at some point, your stream will be done. Your integrator is not called anymore, but you still have one element left that has not been passed to the downstream. This element is stored in your mutable state object. Fortunately, there is one last step in the gatherer API, especially for that. Your third object, the finisher, is called, and it can itself produce more elements. This finisher is a partial integrator. It does not take any element from the upstream, just because there is no one left, and it does not return anything, because there is nothing to call after it. Note that we used an instance of an anonymous class to create the state object. You may be thinking that, oh, this guy must be a nostalgic person that likes using old stuff from the time when he was young. Well, not quite. There is an overlooked feature of these anonymous classes called the non-denotable types. If you use anonymous classes and let the compiler infer the type of the variable you use, and here it's the case because I used var, then you can access the fields and methods that you added to this anonymous class, no matter what type you used to create it. Which is, in that case, very useful. I found this pattern very handy when you need to create mutable wrappers on the fly. And with this instance block, you can even initialize your instance without a constructor. Neat. Let us now use this gatherer in our process. Because you need to give it a specific value for each element you have to insert, creating a builder for it is probably a good idea. So the final pattern of code to create your gatherer is the following. And you can use it to create your new stream in that way. This gatherer object is a little complex in itself, but it also makes your code much simpler and much more efficient. Again, it is still a preview feature, so we'll talk more about it when it makes it as a final feature. So now you can imagine how the solver works. You just take a list of elements. At first, these elements are just numbers, and then you choose 2 of them, merge them with a valid operation, and repeat the process. The question is this approach more efficient than the previous one? Which leads to another question: are we sure that we are not exploring branches of the tree that were already explored and known to fail, as it was the case in the previous approach? And the sad answer is we are sure of the contrary. We are indeed exploring some branches more than once, and sometimes, I should say most of the times, these are failing branches. Let me take an example. Suppose that you have the following set: 5, 4, 3, 2. In the first step, you decide to merge 5 and 4 and apply a subtraction on these items. And then you merge 3 and 2 in the second step with an addition, and that gives you the following state. But in the first step, you also merge 3 and 2 with an addition among other operations. And from there, you will now merge 5 and 4 with a subtraction. So in the end, you have followed two different paths from a given state that took you to the same state. Obviously, the second one is not needed. You don't want to follow it. To prevent that, you need to check if a branch has already been explored for every step you make. So you need to add all the explored branches in a set and check if the set contains the new branch you just built. Fortunately, adding an element to a set and then checking if it contains another branch is pretty efficient, so it's not too bad, it's just a memory overhead. So in the end, the process looks like the following. You get elements and a target. You can first check if there are solutions in your elements, and if there are, then there is no need to continue exploring them. Wrapping everything in records makes your code much more elegant. I use it all the time. If there are elements that are not solutions, then you need to continue. First, reduce them by merging pairs of elements with the valid operations, and you saw all the steps of this process. And then call solve recursively to find the solutions in the new elements you just computed. And at last, get the solutions found and merge them with the solution you got in the previous step. Yes, it's actually as simple as that. How can you compare both algorithms performance-wise? Well, first, you need to understand that it's not 100% relevant to compare them, as the first one is a translation from another language, and this one is built for Java. So let me show you the numbers JMH gave me, and let us draw the right conclusion from these numbers. Be careful, because for the first solution, the results are given in milliseconds, and for the second solution, the results are in microseconds. So there is a factor of more than 1,000 between them. And yes, it's a lot. If there is one conclusion to draw from that, it's the following. Before optimizing your code by trying to unbox your numbers and tweak your list implementations and make your code ugly by using arrays instead of streams, you need to make sure that the algorithm you have implemented is the most efficient one. What these numbers are showing you is that there is a more efficient way to solve the countdown problem than the translation from the Haskell code. And don't get me wrong, Sundar, who is the author of this article, wanted to show that you could translate some Haskell code to Java with the use of data-oriented programming features recently added to the JDK, and that it would give you an elegant and readable code. And that's definitely the case. Maybe the Haskell solution is more efficient when executed with a Haskell runtime because of the way this runtime works internally. And even though the translation to Java is interesting from a pattern point of view, you still need to take a step back and ask yourself if the Haskell approach fits well in a Java runtime. And with this, I'm out of coffee. So that's it for today. Talk to you soon.